speak to you today. Today I'm going to talk about the forbidden pair of graphs to guarantee the existence of Halin graphs. So the Halin graph is constructed from a plane embedding of a tree whose non-leaf vertices have a degree at least 3 by adding a cycle through each leaves in the natural order determined by the embedding. So for example, if you think about star, okay, with at least 3 leaves in here, and by adding a cycle like this, so in the natural order maybe this way or this way, then we can have a Halin graph. So Will is a special case of Halin graph. And if you think about star and here, by adding an edge in here, then we create a triangle. Okay, so actually every Halin graph has at least 2 triangles. So we do not have to talk about okay, let's talk about bipartite Halin graph or triangle pre-Halin graph. It doesn't make sense. Halin constructed this graph as minimally 3 connected graphs. Okay. And the Halin graphs have been named by Lobash and Plummer. This graph has a lot of properties. One thing is Hamiltonian, and another is Hamiltonian connected, which means that for any pair of 2 vertices, there exists a Hamiltonian path between those 2 vertices. And when you delete one vertex, still it's a Hamiltonian. That's one Hamiltonian.
By Hamiltonian you mean cycle?
Hamiltonian cycle, yes. It has a Hamiltonian cycle.
Can you say again Hamiltonian connected?
Hamiltonian connected means for any pair of 2 vertices, there exists a Hamiltonian path in this case. Hamiltonian path between those 2 vertices. So
Start and end, okay.
yeah, from here to here, like that. So this is end vertices, yeah. And by critical, so delete 2 vertices. It has a perfect matching. So minimal means when you delete an edge and then delete 2 vertices, then it's not guaranteed that it has a perfect matching. So that means minimal. Delete one edge, it has a Hamiltonian cycle. And for any edge, okay, there exists a Hamiltonian cycle including this edge and avoiding this edge. And also the Halin graphs have cycles of all lengths except possibly the lengths with even lengths. Okay. Well, we know that the traveling salesman problem is a notorious and complete problem. But if you think about, if you think about in a weighted Halin graph, it's okay. It can be solved in linear time. But Borey, Holton, and Parker proved that deciding whether a graph has a spanning Halin subgraph is NP-complete. So we may be interested in just finding sufficient conditions for a graph to guarantee the existence of a spanning Halin subgraph. Okay, so Lobash and Plummer conjectured every forward connected plane triangulation contains a spanning Halin subgraph. But Chen, Ozeki, and Chichia gave a counterexample. I mean, they found a forward connected plane triangulation without a spanning Halin subgraph recently. But well, even 5 connected, they found 5 connected plane triangles without a spanning Halin subgraph. Yeah, but don't try with the 6 connected plane triangles. You know the reason. Okay. So, well, we maybe wonder, I mean, which classes, I mean, graphs maybe, you know, to guarantee the existence of the Halin graph in here. So,
You mean spanning?
yes, spanning Halin subgraph. So we proved this one. So if it is, of course, it should be three connected, you know. But Halin graph is in three connected. Okay, so it must be three connected. We need this condition, and forbidden pair, those two graphs guarantee the existence of a spanning Halin subgraph.
So this, what does this mean? Forbidden
For
graph?
pre means that this
It can't be
has
subgraph.
this has no but induced subgraph. This has no K13, no P5 as an induced subgraph. Yes.
Induced subgraph.
Yeah. And this condition is best possible in this way. So first thing is
So K13
is just a
means
closed.
no degree 3 vertex.
K13.
Oh no, I see. I see. That's cool.
Scroll.
K13 is this. Well, if you replace this one like a complete graph in here, maybe at least 3 vertices in here, and you can also replace this vertex and this vertex, this was a complete graph, and then add an edge, okay, all between those vertices, and then it has a K13, but it doesn't contain K14. It's easy to check. It doesn't contain K14 in here. You can also show that this is 3 connected, and also P5 free, but even P4 free in here. And you can also show that it does not contain spanning Halin subgraph in here, okay? Because you have to use one. There are 3 vertices in here. One of the 3 vertices must be non-vertex. Halin graph consists of 2 parts, tree and cycle. Okay, and
Each vertex on the top one you connect to.
each vertex. So there are 3 vertices. This is a K3, and we add an edge between all those things, possible things. So for example, if there are 3 in here, so we open here all those 3. So all those 3 like that. Yeah. So it's easy to check. Well, this is 3 connected. K14 free. I mean, if we replace this one with the K14, okay, then still, well, there exists 3 connected K14, P5 free. I mean, without a spanning Halin subgraph. Okay. So I want to show that this condition is best possible, and this is one thing. This is a K14, P5 free, 3 connected, and it does not contain spanning Halin subgraph. It is easy to check this one. Okay. But if we replace P5 with P6, then it's very tough. It was very tough to count the exemplar one. So that looks like this. So shaded region is a complete graph. Okay, and there are at least 2 vertices inside and here. Okay, there are at least, so click has at least 5 vertices. Okay, and you can see there are 6 identified vertices there. And each click has 3 identified vertices, right? So when you pick 2 vertices, maybe different click, in a different click, then there are at least 3 ways to go there from. But you have to use 3 identified vertices in here. Okay, so it is 3 connected. Well, when you delete 2 vertices, at least one of the 3 identified vertices must be exist. Okay, so it's connected. So it's 3 connected, and there's no close in here as in this subgraph. If there is a close, then what happens? So this is called a central vertex. Central vertex must be, well, inside of the clique, okay, one of the cliques, or must be identified vertex, okay. In either case, okay, at least the two leaves must be in the clique. So we cannot have a clone, and we also cannot have a P6. If there exists a 6 vertex path in here, well, at least 3 vertices in here cannot be in the clique, right? Then we have a triangle in here, so that doesn't make sense. And well, we cannot use at least 4 vertices, 4 identified vertices in here. If there are at least 4 identified vertices in here, then we have 3 cycle, maybe 3 cycle, or maybe 4 cycle. Okay, so at most 2 vertices, in a clique, and at most 3 identified vertices. Okay, so you know, we cannot P6, and we can also show that there does not exist a spanning Halin. So if there exists a spanning Halin subgraph in here, well, spanning Halin subgraph consists of 2 parts, the tree and cycles. Okay, and maybe like this. So this is called a non-leaf vertex. Well, just think about the clique in here. There are 3 identified vertices in here, and if those 3 identified vertices, all those 3 identified vertices are leaves, that doesn't make sense. Then how can you move from here? Because the tree is a connected graph. Okay, so at least one of those 3 must be a non-leaf vertex. Okay. And there are 4 cliques in here. So you can check that we need at least 3 identified vertices for the tree. I mean the non-leaf vertices. Okay. And well, I told you there are at least 2 vertices inside of the clique. Okay. And then you can also show that one of them must be leaf. One of them must be leaf. Okay, and there are 4 cliques in here, so we have to use at least 4 vertices as leaves. Okay, I mean for the cycle. Okay, there are 6 identified vertices. We need to use at least 3 vertices for the tree. I mean non-leaf vertices, and we need to use at least 4 vertices for the cycle. This doesn't make sense, so it does not contain a spanning Halin subgraph. So we prove that this, and this condition is best possible. Actually, we proved this one. So this is the main result. Okay, so let me give you a slight flavor of the proof. Okay, I'm not going to prove all the things because there are a lot of cases. So to prove this one, we need this one. So 2 connected closed P6 pregraph is a Hamiltonian. Well, actually there is a complete characterization to be Hamiltonian for a 2 connected forbidden pair of graphs. Okay, you can check. But anyway, so if there is a dominating vertex V in here, then well, we just can have, if there is a dominating vertex in here V, so it dominates all the vertices in here, then well, because if you delete vertex V, this is 3 connected. If you delete V, then at least that's 2 connected. Okay, and this also K1 through P5, so it may satisfy this one. So we have a Hamiltonian. So we can have a cycle like this when you delete this one. So this is so then the graph has a spanning wheel. I mean, spanning wheel is also spanning Halin subgraph. So we can assume that there are no dominating vertex. So now we can think about smallest separating set in here. So here's S. So we choose this is the smallest separate, not just a separating set, smallest separating set, and then well there might be a lot of components in here, but we can show that there is only just the two. Okay. So first, for any vertex B in here, in the set S, okay, and this vertex and V sub I, well, let's say this is V sub 1, maybe V sub 2, maybe more, okay, then it's always non-empty. So there is a intersection. So if you pick a vertex in here, it always has a neighbor in each V sub I. If it's not, then just, we can have a smaller separating set, right? So, and so well by this one, we can show that this is K2, because if there are more. Because this vertex has a neighbor in here, if there are more than two, then we have a clone. So, yeah, so there are almost two, and exactly two components in here. And now, this is the key idea actually to prove. We think about the vertex subset as sub I, okay, in here. Maybe they may be overlapped, it may be possibly, okay? Maybe overlapped, possibly. So this vertex in this set, the neighbor, this one, is all in here. The neighbor of this vertex contains all vertices in here and V sub I. So that is called S sub I, okay? And we can prove that the union of those two is just the S. If there is a vertex, maybe not in here, that means this vertex, okay, because every vertex in S has a neighbor on both and here, okay? But, if this vertex is not in here and here, then, well, maybe some vertex is not adjacent in here. This one is also not adjacent here, okay? So probably we can find the vertex which is adjacent. This one may be like that. P5. Yeah. So S is the union of S1 and S sub 2. Oh no. How can I back? Sorry. Thank you. And you can think about the graph induced by S sub 1 or S sub 2. This has the independence number is m most 2. Because m most 3, then what happens? We have a clone. Yeah. And this vertex, the neighbor of then here is a clique. If it's not a clique, then what happens? If it's not a clique, then it's not the same those two. Okay,
Oh, another clue.
we have a clue. Yeah. And A is in here as sub I, inside S, maybe in here as sub I. And GA is connected, then GA is a Hamiltonian, GA has a Hamiltonian path. Because we think about X, vertex in here, adjacent in here. Then this is, because this is connected, we assume that GA is connected. And then vertex in this one is adjacent to all vertices in here. That means that the two connected guarantees Hamiltonian path.
That's because of the previous theorem.
Yeah. And A is an S. So you can think about just A is an S in here. Maybe some subset in A. Well, if the neighbor of this is the same, the neighbor of this one is just pre sub I, then, well, this and this is the same thing. So there is nothing to do, nothing to prove. So if this is not the same thing, so like this, so maybe this is not empty, like that. So this is NA, neighborhood in here. And now this guy is just A, and this is S minus A, right? Then this one and this one together is also separating set. Because this has no neighbor in here, right? So together those two are separating set. So S minus A union, so this is actually NA intersection with sub 1. Okay? So NA intersection with sub 1. But this is greater than or equal to S because we chose this one, the smallest one. But they are all separate. This is S minus A and plus NA intersection with sub 1 in here. But this guy, see this one? This is S minus A. Oh, S is cancelled. No. Then we have it. Oh, sorry. Then we have this inequality. Well, now let's talk about this case. So this is not empty. Maybe it may be overlapped in here. Okay, so this is S sub 1, this much, and S sub 2, maybe this much. Okay, the non-empty. This means that V sub 1 and V sub 2 are cliques. Okay. See, this is clique. We show that the vertex V in here, and this is a clique. If this is not clique, then we have a close. Remember?
Yeah, but that's in the neighbor of some vertex in S, right?
Yes, but this is non-empty, both non-empty. Both non-empty mean that this is adjacent to all like that, and this one is adjacent to all.
Oh, I see.
Yeah.
Definition.
Yeah. This is, yeah, it's a clique. Big condition, okay, to guarantee the existence of the Halin graph. Okay. But anyway, so, so let's talk about this case. Actually, the other cases we need more conditions, actually, more properties. But today I'm just going to talk about this case. Okay, so so I want to partition this S. Well, they may be overlapped S1 and S2, but I just want partition just S, okay, and S sub 1 prime and S sub 2 prime in here, like that. But and S1 prime is just in S sub 1, S sub 2 prime is in, but they are not overlapped. It's those two guys. Okay. Okay. And well, we know that it's 3 connected. So the size of S is greater than or equal to 3. So well, we may assume that one of them is bigger than. If the size is greater than or equal to 2. So say this one is greater than or equal to 2. And so let's pick one vertex in here. Okay. This is V. Okay. And well, if this is connected, okay, then in this one connected, then that means that it has Hamiltonian. No, I'm sorry, not Hamiltonian. Hamiltonian path. Okay. And well, if this is not connected, maybe 2 parts in here, but because this is complete bipartite, and this part, complete bipartite in here. So if this is not connected, then it must be complete graphs in here, because independence is at most 2 here. Okay. So this means that this part is covered by at most 2 paths. Okay. So say this one. Okay. I have a better picture in here.
So this partition S1 and S2, S1 prime.
S1 prime, S2 prime partition.
It's just arbitrary partition.
Arbitrary partition, yeah. So we have a V in here. Okay. And this is A, this is B. This is C, and this is D. And most 2 means that, one of them must be maybe empty, possibly. Okay, then maybe this one is just empty. Okay, assume that. Okay. And similarly, we can also prove that the GS1 just prime part can be covered by at most 2 passes. So I'm going to have this is E, F, and here is G and H. Okay. Okay. And we're going to use this one because V and here, A and here. Well, because at least 2 vertices in here, then this guarantees that there are at least 2 neighbors in here. So I will take this one. A is adjacent to this one. This is Y sub 1. And take this one is Jack sub 1 in here. Okay. And well, by claim 1, we know that every vertex has a neighbor in here. So Y sub 2 is instant in here. So it's Y sub 2. Because every vertex has a neighbor in here. So we can have this one. Okay. Now we pick X sub 2 just in here. But of course, this is adjacent to this one, because this is S2 prime part, so it adjacent to all vertices in here. So there is an edge between those 2. And so our goal is to find a spanning Halin subgraph. But Halin graph consists of 2 parts, a tree and cycle. A tree, well, so we need to find, it is called actually Heath, but anyway, we need to find non-linear vertices adjacent to all other vertices. Then we have to get a tree like that. Okay, so this X sub 1 and V and x sub 2 is, this is the key purposes actually to find the spanning tree and a cycle, okay? Because, well, this vertex, because this is clear, so this vertex adjacent to all vertices in here. At least 3 vertices. I didn't finish it yet. This adjacent to all vertices in here, but this also adjacent to all vertices in here because this is S sub 1 prime. This is S sub 1. So S sub 1 and here there are complete bipartite graphs in here. So this vertex adjacent to all in here. Okay. V is adjacent to all in here. And X sub 2 adjacent to all in here because this is S2 prime. There are complete bipartite graphs in here. So those 3 vertices consider all vertices. Okay. Well, so I can draw something out more in here. So it actually looks like there is one more vertex because we assume that each side has at least 3. So we can also think about G sub 1 in here. Okay. And because this is S1 prime, so it adjacent to this one, right? Of course, this is also adjacent in here. I'm creating cycle, including all vertices except those 3. Okay, that's my goal. Okay, and so this one is also adjacent to this one. Okay, and then so we also think about the G sub 2 in here. Of course, these are adjacent because it says 2 prime in here. Okay. The remaining part, maybe this one, there might be a lot of vertices, not exactly 3. So we just think about because this is a clique, so we just think about the path, including all vertices starting from Y sub 2, except those 2 vertices. Okay, so these are all vertices in here except those 2. Okay, and then we add in here. See? I'm sorry, I made a mistake in here. So I need actually this one includes all paths, and I need the path. This because this is a clique, so I need the path including all vertices except those 2, starting from G sub 1 in here, and now we add in here. Sorry. Yeah. So those cycles including all vertices, right? All vertices except those 3 in here, right? So this guarantees that the existence of a spanning Halin subgraph. Well, you are not probably sure about the planarity in here, right? But it is okay because the neighbor of this one in here is a path. This one is also a path. And this guy is also pass. So if there is a pass, then maybe you can switch and then you can make it. So it is okay. Well, so this is just one case. Well, there are a lot of cases. So I just want to give a slight flavor of the proof. So, okay. And then I want to skip the other part. But so we just found some sufficient conditions to contain a spanning Halin subgraph. So you may also think about, you may also think about other sufficient conditions. But do not try with a forbidden pair of graphs because there is a project team and well, they almost done, so don't try. But you can think about the triple condition, probably triple pair. Okay. Maybe you want to start, well, I couldn't find the paper, but in some paper, the author just said that there is a complete characterization for triple things, XYZ free graph, to guarantee the Hamiltonicity. Okay, so because Halin graph is a Hamiltonian, okay, so at least you should start from there. Okay, and well, Halin graph is very strong, probably, and has a lot of properties because probably. It may be because of the planarity, probably. So if we destroy the condition, the planarity there, then what happens? Okay. So let me give a definition. So generalized K-Halin graph is a graph. It's constructed from a plane, constructed from a tree, not plane invading there. So we deleted that condition, okay? But this condition is almost same, but we'll put K in here, and so non-linear says degree at least K in here. Well, the same thing, we add a cycle through each ellipse in here. This definition created by us, so you couldn't find a line. But anyway, then what happens? Well, and we actually prove, well, Guantao and Shoichi and I proved something on matching number. Well, you remember the Halin graph has a property. If you when you delete two vertices, it still has a perfect matching. I mean, if it has an even number of vertices, okay. But if we delete the condition planary, then it has no perfect matching. I mean,
Which condition?
planarity.
Planarity.
Well, yeah. So Halin graph started from a plane embedding of a tree, right? But we delete that condition. Yeah. Then it has no perfect matching. So when we try to find a lower bound for the matching number, I mean the worst case, and we did that. And other things. So no perfect matching. And so of course it's not Hamiltonian. So because it's not Hamiltonian, you can also think about maybe lower bound, maybe for the circumference of a generalized K-Halin graph also. Okay, we tried, but we don't know because well, if you think about just the cubic, and anyway, if there is a spanning Halin subgraph, then you know, if you think about spanning Halin graph, then you know, the number of ellipses is at least n over 2 plus 1. So circumference is okay. That's easy to find the upper bound. For that, lower bound, that one. That's n over 2 plus 1. But it's a trivial thing. Well, can you find other things? That's probably hard. Well, we tried. We thought that that's a 2 1/3, but well, the proof is wrong. I don't know. Well, you can try. And also girls. Remember, the Halin graphs is almost pancyclic. So I mean, so the girth is just always 3 because it has a triangle. But in this case, is no. I mean, you know the general, you know Peterson graph. Peterson graph is a generalized, actually generalized 3 Halin graph, and we know that the girth of Peterson graph is 5. Okay, so we also tried to find the upper bound, not lower bound, for the girls in here. Well, we didn't find any bound for this one. I just guessed that maybe the bound is constant. Or maybe logarithmic. Yeah. Okay, this is all for. Thank you for your attention.